Welcome to the third lecture of module 1 on chemical reaction engineering 1. In this module we are discussing chemical kinetics, and in this lecture we will discuss temperature dependency and testing of kinetic theories. Before going to this lecture, let us have brief recap on our previous lecture. The topic which we covered in our previous lecture is ideal reactors, and we have seen there are three different types of reactor: batch reactor, and then flux flow reactor, and continuous stirred tank reactor. Then we have discussed reaction rates, rate constants and its unit. We have distinguished between elementary and non-elementary reactions. Then we have seen what is the concept of order of the reactions and different rate laws, then molecularity of the reaction and different rate law which derived from the elementary reactions. Now, in this lecture we will consider kinetic models and temperature dependency. So, the brief outline of this lecture are kinetic model for elementary reaction, kinetic model for non-elementary reactions, and then we will discuss the kinetic models, and finally we will discuss temperature dependency term of rate equation. So, kinetic model for non-elementary reactions. As you know, for elementary reactions there are series of reactions which take place, and finally we obtain the product. Some products we call the intermediate products, for which we do not see the change of concentration, or that is not stable compound, and then that disappears. So, its concentration present in the system is very minute quantity. So, intermediates only present in very minute quantity. So, that is why it is very difficult to observe in the reaction system, and only we observe the initial reactants and final products. If we consider a single reaction, say A2 reacts with B2 and produce twice AB. This reaction is non-elementary reaction. So, to explain the kinetics of these non-elementary reactions, we can assume these reactions can take place with a series of reactions. Suppose the kinetics may be assumed like this: A2 can dissociate reversibly to twice A star, and then A star reacts with B2 form AB plus B star, and A star reacts with B star form AB. So, if you look into the overall reaction, you can see that this cancelled out, this cancelled out, and you will get A2 plus B2 forming twice AB, and this star represents intermediates. Kinetics of this reaction, the intermediates can be grouped in 4 different categories. One is free radicals, then second one is ions and polar substances, then molecules, and then transition complexes. Now, free radicals, these are basically free atoms or fragments of molecules which contains one or more unpaired electrons. They are called free radicals. These free radicals, sometimes it may be stable compound or stable intermediates, sometimes they are not stable. In most of the cases, free radicals are very unstable. One of the example of relatively stable intermediates is the triphenyl methyl. So, this is triphenyl methyl, and this dot represents the free radicals. So, for free radicals we generally represent it by dot. Okay. Some of the examples of highly reactive free radicals are methyl CH3 dot, C2H5 dot, H dot, CCl3 dot, I dot, and so on. So, these are highly reactive radicals. Now, ion and polar substances, fragments of molecules and electrically charged atoms, they are called ions or polar substances, like sodium plus, then OH minus, H3O plus, NH4 plus, I minus, CH3OH2 plus. So, these are very active ions or molecules, they can fragments of molecules, they can act as reaction intermediates. Now, molecules. In some of the reactions like series reactions, the intermediate molecules are not stable, it immediately dissociates to products. So, the intermediate molecules is not observed or its concentration is difficult to measure because of the amount of intermediates observed at a particular time. So, very minute quantity of the intermediate present which cannot be determined physically or experimentally. That is why those are called the intermediate molecules. Like if we consider the consecutive reaction A to R to S, here the reactions is multiple reactions and these R is called intermediates. One of the example of this is dimethyl ether dissociates to CH4 methane plus formaldehyde and then its form CO plus methane. So, this is K1, this is K2. So, these are very unstable intermediate. Another example is epoxides or ethylene oxide. It dissociates to form CH3CHO and then it dissociates to CH4 plus CO. So, this is one of the examples of molecular intermediates or reactive intermediates. Another example of radioactive decay like lead, it form bismuth and then it dissociates to decay to polonium. So, this is radioactive decay. So, these are examples of reactive intermediates. Now, transition complexes. Collision among different reactant molecules lead to distribution of the energies and molecules then either decompose to give products or can return to the normal state. Such unstable forms are called the transition complexes. That means, when the molecules are in always Brownian motion in a particular system and they collide each other. Once they collide each other, they lead to distribution of the energies among the molecules present in the system. Some molecules, because of its energy states, it's converted to the product, or some molecules due to further collisions it comes down to the ground state or the normal state. The complex which formed due to the collisions is known as the transition complexes. In most of the gas phase reactions, occurs via transition complexes. This reaction schemes occurs via the two different mechanisms. The postulated reaction scheme involving four kinds of intermediates can occur with non-chain reactions and then chain reactions. So, non-chain reactions are basically molecular intermediates and transition complexes, and then chain reactions basically free radical reactions. So, in a non-chain reactions, the intermediate is first formed and then it disappears to give the products, like reactants it formed intermediates then intermediates dissociates and give products. One of the general examples of non-chain reaction is the enzyme catalytic reaction. Very well known reactions, enzyme catalytic fermentation reactions, like if you have A and producing R and with the catalyst enzyme, the experimental rate can be obtained. RR would be equal to K into concentration of A into initial concentration of the enzyme divided by Cm is a constant plus concentration of A. So, this reactions is viewed to proceed via the following mechanisms. A reacts with enzyme and form a enzyme complex. And A enzyme complex dissociates to form R plus enzyme. So, another examples of non-chain reaction is the transition complex mechanism, like decomposition of azomethane. So, CH3 whole to N2, it decomposes to form C2H6 plus N2, and the reactions can occur in various conditions. In one case it may be first order, in other case it may be second order, and so on. So, the reaction for this case is explained by Lindemann first in 1922 with the reactive intermediates, and the mechanism is proposed as follows: A plus A form A star plus A, that is formation of energized molecules, then A star reacts with A, it form A plus A, that is forming the stable compound, and we can view it the reverse reactions of this, the first one. That means, the activated complex or active energized molecules again collide with A molecules and coming back to A plus A. So, it is the reverse one, and then the third step is the spontaneous one, that is A star decomposes or giving the products R plus S. So, this overall reactions can be viewed as A2, so A2 is forming A star and then forming R plus S. So, now chain reaction, the chain reactions in which the intermediates which form first and then it's initiate the process of the next steps. So, the reactions proceeds via different steps, that is reactant, it first form intermediates and this step is called initiation. Then intermediates reacts with reactant again, it form intermediate plus product, and this step is called propagation. And the third step is intermediate forming products, and this step is known as termination. So, most of these chain reactions goes via free radical mechanism. Let us consider the reaction mechanism for the reactions of bromine with hydrogen forming hydrogen bromide. So, the reactions of hydrogen plus bromine is forming twice HBr, and the experimental rate for this reaction is observed as RHBr is equal to K1 concentration of hydrogen into concentration of bromine to the power half divided by K2 plus concentration of HBr into divided by concentration of Br2, and the reactions involves the following mechanisms. The bromine first dissociates into Br radical. This is also initiation and termination. Br dot reacts with hydrogen, it form HBr plus H dot. This is called propagation. And the third step, H dot plus Br2, it form HBr plus Br dot. So, this is also propagation. So, the example of formation of hydrogen bromide from hydrogen and bromine is one of the example of chain reactions which goes through the free radical mechanism. So, now we will discuss the testing of kinetic models. There are two issues involved for the testing of kinetic models. They are the reactions may proceed by more than one mechanism with reactive rates that may change with the conditions. And the second one is more than one mechanism may be consistent with the kinetic data. So, resolving these issues is quite difficult, and let us not consider these issues over here, and let us consider a simple system based on our knowledge. If we developed a kinetic model and whether that is valid with our experimental observations. So, let us look into that part first. So, there are two type of intermediates we can consider, or two type of elementary reactions we can propose for any kinetic model. In type 1, the intermediates is unseen and unmeasured because of its quantity present into the system is very less. Suppose if we consider an intermediate X which present in very small quantity. So, its rate of change of concentration of this particular intermediate can be taken as 0. That means, d Cx dt would be equal to 0 when concentration of X is small, and this is called steady state approximation. To understand this mechanism or the kinetic model, please go through the book of Cooney and Levenspiel and try to, there is some example given, and try to understand this model. In type 2, the consider the homogeneous catalyst concentration is C naught. So, this present in two forms, free catalyst or combined with intermediate X. Now, we can consider the total concentration of catalyst would be equal to the free catalyst concentration plus the concentration of the catalyst with the intermediate. And in this case also we can assume dCx dt is approximately equal to 0. So, the reactant A reacts in presence of catalyst and form intermediate X. Where the equilibrium constant can be denoted as K1 by K2 which is equal to concentration of the intermediate divided by concentration of A into concentration of the catalyst. Now, let us take an example to test this kinetic model of type 2. A substrate A is converted to product R by the reaction of an enzyme as per the following: A to R in presence of enzyme. Many of these reactions exhibit the following behavior: a rate proportional to the concentration of the enzyme introduced in the mixture, that is C naught. At low concentration, the rate is proportional to the reactant concentration Ca, and at high concentration the rate levels off and becomes independent of the reactant concentration. So, these are the typical behavior observed in most of the enzymatic reaction. So, now we need to propose a reaction mechanism to account for this behavior. This is the one of the examples which is solved first by Michaelis and Mentgen in 1913, and Michaelis got Nobel Prize in chemistry. So, they proposed the reaction scheme like this: A in presence of the catalyst forms the intermediate X, then X form R plus E. With the two assumptions, we can write concentration of E naught would be equal to concentration of E plus concentration of X, and d concentration of X dt would be equal to 0. Now, if we write for this reaction X to R plus E, if we write the rate equation, it would be d concentration of R by dt would be equal to, suppose this is K3. So, this would be K3 into concentration of X, and d Cx dt would be equal to K1 into concentration of A into concentration of E minus K2 into concentration of X minus K3 concentration of X would be equal to 0. So, the first reaction is A plus E, which is reacts reversibly from intermediate X. So, this is K1, this is K2. Now, from these two we can write concentration of X would be equal to K1 concentration of A into concentration of E naught divided by K2 plus K3 into plus K1 into concentration of A. Now, if we introduce the concentration of X in the earlier equation, that is d Cr dt is equal to K3 into concentration of X, and we have obtained concentration of X is equal to K1 into concentration of A into concentration of E naught divided by K2 plus K3 plus K1 into concentration of A. So, now if we substitute this Cx over here, we would get K1 K3 Ca into Ce naught divided by K2 plus K3 plus K1 into concentration of A. So, we can write this is K1 K3 into concentration of A into concentration of E naught divided by K2 plus K3 divided by K1 plus Ca, which we can write as K3 into Ca into Ce naught divided by Cm plus Ca. This Cm is nothing but K2 plus K3 by K1 and is known as Michaelis constant. So, by comparing with the experiments, it can be observed that minus d Ca dt would be equal to dCr dt, which would be proportional to E naught, as can be seen from this equation. So, if we write dCr dt is equal to K3 concentration of A into concentration of E naught divided by concentration of M plus concentration of A. This is would be proportional to Ce naught and it would be proportional to concentration of A when concentration of A is very greater than concentration of A. So, if this is very greater, from this we can write dCr by dt would be equal to K3 into Ca into Ce naught by Cm. That means, K3 into Ce naught by Cm can be clamped to a constant and it would be proportional to Ca. So, that is valid when Ca is very less than Cm, and it would be independent of concentration of A when Ca is very greater than Cm. That means, when this is very greater, so this can be written as d Cr by dt is equal to K3 Ca Ce naught by Ca. So, then this will cancelled out and it would be K3 Ce naught. So, that means, it would be independent of concentration Ca. Now, the temperature dependent term of the rate equation, as we have seen particularly for the elementary reactions, the rate expression can be written as the function of temperature as well as composition. That means, R is equal to function of temperature into function of composition. Or we can write this function of temperature is included with the term K, the rate coefficient, into function of composition. The temperature dependent term can be related with the activation energy, and the equation is K is equal to K naught into e to the power minus E A by R T, where K naught is the Arrhenius frequency factor and E A is the activation energy. R is the universal gas constant and T is the temperature. Now, if we take the logarithmic of this relation, that is K is equal to K naught e to the power minus E A by R T. If we take logarithmic of this, it will be ln K is equal to minus E A by R into 1 by T plus ln K naught. Now, if we plot ln K versus 1 by T, this will lead to a straight line. and slope would be E A minus E A by R. The value of R is 8.314 joule per mole Kelvin. So, the activation energy, that is E A, can be calculated using the two values of rate constants, say at temperature T1 and at temperature T2. So, we can use the expression ln K2 by K1 would be equal to minus E A by R into 1 by T2 minus 1 by T1 or ln K1 by K2 would be equal to E A by R into 1 by T2 minus 1 by T1. T is in Kelvin. Now, let us compare the temperature dependency of the Arrhenius equations with the different theories. Like if we consider theories, they generally represents the rate constant K is equal to K naught dash T to the power m e to the power minus E by R T, where m is equal to greater than equal to 0 and less than 1. So, this equation predicts most of the cases for the rate from collision and transition state theories. These are temperature dependency on the rate constant. Now, the temperature dependency of the pre-exponential factor is too sensitive, and so the exponential term of temperature dependency is too more sensitive than the pre-exponential factor. So, that means which is shown over here, this is not so sensitive compared to the temperature sensitivity of the exponential term. So, this can be expressed again with K is equal to K naught e to the power minus E A by R T. Now, if we plot, it will give K versus 1 by T, and this is say at low temperature, say at 375 Kelvin, 376, this is at 463, and this is in the range of 2000 and 1000, and this is the K values, that is 5, 10, 20, 50, then 100 and 200. So, if we plot the Arrhenius equation, it would be like this. This is with slope E by R. So, this is the slope. Now, activation energy and the temperature dependency. From the Arrhenius plot, it can be seen that the plot of ln k versus 1 by T gives straight line. With large slope for large E activation energy and small slope for small e. Secondly, reaction with high activation energy is very sensitive and reactions with low activation energy is less sensitive. Third thing is that at any reaction is much more temperature sensitive at low temperature compared to at high temperature. Reaction is more sensitive at high temperature than low temperature. And the frequency frequency factor, the pre-exponential factor is not much temperature sensitive. So, these are the relations or the sensitivity of the activation energy with the temperature. Now, just let us calculate the activation energy for a simple example. A second order reactions was observed and the reaction rate constant at 10 degree was found to be 1.5 into 10 to the power minus 2 liter per mole per second, and the other temperature at 40 degree centigrade 8.5 into 10 to the power minus 2 liter per mole per second, and we need to calculate the activation energy of this reaction. So, step 1, we need to just calculate the convert the temperature into the Kelvin, that is T is equal to degree centigrade plus 273.15. So, it would be 10 plus 273.15. So, it is 283.15 Kelvin, and T2, this is T1, T2 would be 40 plus 273.15. So, it would be 313.15 Kelvin. Now, we need to find activation energy. So, to do that, use the equations ln K2 by K1 would be equal to EA by R into 1 by T1 minus 1 by T2. So, if we substitute, this is ln 8.5 into 10 to the power minus 2 divided by 1.5 into 10 to the power minus 2. So, this will lead to EA divided by 8.3145 joule per Kelvin mole into 1 by 283.15 Kelvin minus 1 by 313.15. So, if we solve it, it will be ln 5.67 would be equal to EA by 8.3145 into 3.38 into 10 to the power minus 4. So, from here you can calculate EA is equal to 4.263 into 10 to the power 4 joule per mole, which is equal to 42.63 kilojoule per mole. So, this is how we can calculate the activation energy knowing the rate constant at two different temperatures. So, thank you for hearing this lecture, and we will continue our discussion on the kinetics and the reactor design in our next lecture.